Delivering a multi-billion-dollar offshore platform means dealing in extremes. We are suspending thousands of tons of steel in mid-air, over open ocean, operating at zero margin for error. Execution on this scale requires aligning two entirely separate realities that move at different speeds: the paper world of design and the steel world of fabrication. The paper world is quiet and abstract, built of process simulations, spreadsheets, and diagrams. The steel world is loud, heavy, and industrial. It is a physical reality of massive orange gantry cranes, dense vessel hulls, and thousands of welders working in a shipyard. Your absolute prime directive as a project manager is straightforward. Ensure the paper world arrives at the steel world early enough and accurate enough to actually be built. Every single physical component in that shipyard, every valve, every pipe, and every pump traces back to one specific origin, a theoretical number describing a fluid nobody has even produced yet. We have to understand how a single pressure or temperature reading dictates the exact geometry of 10,000 tons of structural steel. To find the answer, we trace that single thermodynamic number through a rigid sequence of documents, watching it evolve until it becomes a welded pipe. Mastering this engineering sequence is the only way to protect your budget. If you lose control of this information flow, you will be forced to fix mathematical errors in heavy steel 2 years later at 100 times the cost. The paper world begins with the digital model. Before anything physical exists, engineers build a computer simulation of how the unproduced reservoir fluid will behave as it moves through the future plant. This simulation defines the physical boundaries of the project. It dictates the fluid volume, the maximum temperatures, and the extreme pressure constraints the facility must contain. The formalized output of that simulation is the heat and material balance, or the H&MB. The H&MB exists as a dense matrix of raw data. It populates every stream and phase in the facility with the specific thermodynamic properties required for design. This matrix acts as the parent document for the entire project scope. Locking in these numbers freezes the baseline assumptions for the project. Every subsequent engineering discipline will build their detailed designs strictly on top of this data. A miscalculation in the heat and material balance compromises the mathematical foundation of the project before a single blueprint is even drafted. Once that parent data is locked, it generates the first set of downstream child documents. The first of these is the equipment list. This document serves as the definitive ledger for procurement. It tells the team exactly what major hardware, compressors, separators, and generators, is required to handle the fluid defined in the simulation. The second child document is the process flow diagram, or PFD. This flowchart maps out the conceptual logic of the plant. It connects the major equipment pieces in sequence, but it does not yet include physical routing or safety instrumentation. Think of the PFD like an estate agent's high-level floor plan. It shows you where the rooms are, providing a conceptual understanding of the space without the technical detail needed to build it. The fabrication yard cannot use a concept. To construct the actual modules, the yard needs exact physical dimensions, structural coordinates, and precise connection points. While the process flow diagram and the equipment list frame the conceptual boundaries, the yard cannot cut steel based on a concept. To bridge that gap, the PFD must evolve into the most critical document in the engineering sequence, the piping and instrumentation diagram, or P&ID. At this stage, the engineering detail explodes in complexity. The simple lines and blocks sprout specific valve tags, instrument bubbles, and exact pipe diameters. We have moved past abstract flow. The P&ID dictates the detailed safety logic loops and the individual tags for thousands of unique instruments. The P&ID serves as the master technical record, fixing every valve and instrument tag into a finalized specification. Every other discipline relies on this document. Electrical, structural, and instrumentation teams are unable to start their detailed design work until the P&ID is locked. Finalizing these diagrams require thousands of engineering man-hours and intense coordination across multiple teams. When a P&ID is issued, it releases workfront, the specific tasks and instructions that keep the fabrication yard moving. The P&ID is the primary bottleneck of the project. Without it, the engineering teams and the yard workers are stopped, waiting for their instructions. Consider a common hazard in this sequence. A client requests a minor 5% throughput increase after the PFDs have already been issued. It is easy to assume this change is cheap because no steel has been cut yet. Looking at the document hierarchy, that 5% change strikes the heat and material balance at the very top. Because the parent data has changed, a wave of invalidation cascades downward through every child document. The shockwave hits the P&ID. Line diameters must now expand to handle the new fluid volume. It hits the equipment list. Pumps must be resized and safety valve capacities must shift to handle higher operating pressures. It hits the budget. Any purchase orders already placed for the original equipment instantly become expensive change orders. A minor tweak on paper translates to a six-figure financial hit and a systemic schedule delay in the physical yard. This is the logic of the document cascade. Because the H&MB is the parent, altering it forces a mandatory revision of every single child. Getting these documents right is only the first step. Next, we will look at the 4 revision stamps a P&ID must pass through before a yard is allowed to act on it. Successful project delivery depends on aggressively defending this engineering sequence. Mastering the rigid flow from paper to steel is your primary mechanism for protecting the baseline.